Trig, Saxon's Trig, Lesson 2. This is now sections C and D. C deals with cones and pyramids. So we've been talking about area being the distance that it takes to cover the bottom of a surface, and then volume is how much it takes to fill the bottom of it and then take it in layers up to the top. So how much does it take to fill the entire shape? And surface area, which is how much it takes to cover the top, the bottom, and the area of the sides. And then lateral surface area is just what it takes to cover the sides themselves. All right, in cones and pyramids, these things come to a point, and so their volume is going to be adjusted. You see, they do a review of the right solid, right cylinder terms, which you already know. And then it goes into the dark words, which they then repeat in the box. Volume of a cone or a pyramid. So what you want to do is take the overall volume of the solid shape that it would be in. So if you are picturing that you have a cylinder and then you bring it to a pointy top, the bottom has not changed, but the top has gone to a point. And that is turning it into then a cone or a pyramid, depending on what your base shape is. So you're shearing off a part of it. So you're going to find the volume as if it were in its solid format, and then you're shrinking it down to the point. And that memorized fraction of shrinking it down or shaving it off takes it down to 1/3 of the rest of the volume. And that's what it says in the box. The volume of a cone or pyramid equals 1/3 the product of the area of the base and its height. So in other words, find the regular volume and multiply it by 1/3. So 1/3 area of the base times the height is your overall basic formula that you need to use for cones and pyramids because they come to the pointy tops. If you then move on to the example on page 20, example 2.3, they have given us a base shape. This one is more rectangular with the semicircle again here with a radius of 1. This side is 3, this side is 2. So we are going to, and it says the base of the cone is shown as I've drawn it here. The dimensions are in meters. If the cone is 6 meters high, find its volume. So we know we're doing volume. I guess I'll put equals volume. So we're going to do the area of the base, which is a rectangle and a semicircle. So the area for the rectangle is 3 times 2. And then the area for the semicircle is half the area for a whole circle, pi r squared. The radius is 1, so 1 squared. So again, this was the area of the rectangle, 3 by 2. The semicircle had only half of the full area, pi times radius squared. So then this is 6 plus 1 squared is 1. 1 times a half is still a half, so a half a pi. And on the calculator, you can turn that into a decimal. Make sure I'm pulling the right one. Yes, 7.57 meters squared for the area of the base. Then we're going to multiply that by the height, which we found in the paragraph was 6 meters high. And then we are going to take 1/3 of that. And so you're going to take that answer basically and divide it by 3 or punch them on your calculator. But however you do it, you should be getting 15.14 meters. Now, let's discuss what is the exponent for volume. We've done area. Area is always squared, but volume is always cubed because you've done area of the base, which turns it into meters squared, and then you've multiplied by another part, the height, which is why you're multiplying 3 things. So that's why it ends up being meters cubed. So any volume answer must have meters cubed with it. Okay. Then we have surface area for the cones. So we've just done the volume. Now let's do surface area. We know that that is the area covering all of the parts. So since it's circular, we know the base is going to be a circle, but the sides are more like your ice cream cone. So it's like the cone part itself that you're eating. That's its lateral surface area, and it's obviously a very unique shape. So it's going to require a very special formula to get the lateral surface area, and that will be pi times the radius times a slant height, which is a cursive L. Now they don't do theirs, you'll see in the book it's more like an actual little L, but I'm always going to do it this way so that I don't get it confused with the number 1 or something else. So for the lateral surface area for a cone, you are dealing with pi times radius times slant height. You can, as they show there at the bottom, have oblique circular cones or right circular cones, unique shaped circular cones. They also clarify a new term, which is that this top peak is actually called the apex. Again, we cover it here, but we don't use it throughout the book. And the same thing, no, not same, similar. When I shift from cones to pyramids, you don't have a unique formula because it's not a unique shape. On page 21, you see that all of the sides of triangular pyramids are triangle shapes. So what we're going to do is find the area of those individual sides and combine them together, or use the shortcut for the lateral of the perimeter times the height. Okay, now that you've got those terms, and I don't think I skipped anything dark that was of importance, example 2.4 on page 21 asks us to find the surface area for the provided cone. All right, so I'm going to reuse this shape here because that's a cone. Theirs in the picture is a lot like more squished, less height. The radius of the base of the right circular cone is 8. The radius is 8. The slant height, now that's going to be the side here, and that's what that slant height stood for. I didn't tell you that before. That is 10 centimeters. And it wants to find the full surface area. So we're going to begin with finding the area of the base of the circle. Since that's a circle, we are going to follow the formula pi times radius squared. The radius was 8, so 8 squared. Area of the circle is the base, plus for full surface area, we need all of the sides. The sides follows this formula, pi times the radius, which is 8, times the slant height, which was given at 10, and that's the sides. So the bottom and the sides, total surface area has been provided. So 8 squares to 64, and 8 times 10 is 80. So this one, most of the time they're multiplying with the pi, and probably to put it in decimal, they did not in this example. So whether you do or don't put it in decimal, it's fine. I can do the conversions when I'm checking your work. That's not an issue. But in this case, since it was in an easy enough pi to add, they decided to add it to 144 pi, making sure I have those numbers right. Yes, okay. And then what were our dimensions in centimeters? And because it was surface area, it's going to be squared, and we're going to, I would technically box that answer. Example 5. The volume of a right circular cone is 6 pi centimeters cubed. The height is 2 centimeters. Find the radius. Okay, so now we're almost working backwards because they told us the volume was 6 pi. And the volume had dealt with it, shaving it off at a third, area of the base times the height. So this 6 pi equals 1/3 the base, and I'm implying area there, area of the base times the height. What else did they give us? Height is 2 centimeters, so this can be substituted in for 2. So we need to work backwards to find the area of the base, and then from there find the radius. So we're going to actually make this 2/3, so 6 pi equals 2/3 and then the area of the base. To remove this 2/3, which is multiplying, we're going to divide. When you divide a fraction, you should remember from your algebra studies that that means you flip and multiply when you take it to the other side. So this is going to become 3/2 times 6 pi. To avoid confusion, since I'm handwriting it, I'm going to go ahead and turn it into a fraction by putting it as a base of 1. And then I can reduce in my head. 2 goes into 6 3 times. 3 times 3 is 9. So this is now 9 pi is the area of the base. Now, what was the base shape? A circle. So how do I find the area of the base? What was that formula for the area of a circle? Pi times radius squared. Now there's a pi on both sides, which means that when I divide them, they cancel each other out. And the radius squared is 9. What number multiplied by itself is 9? The radius is 3. And dimensions here were all in centimeter. And this is a radius, a straight line from the center out to the edge of the circle. So it's not going to be squared or anything else. It just works out to be 3 centimeters. Example 6, page 22. The base of a regular pyramid is a square. Base is a square. Oh, those should be identical. And then they're coming up to a point at the top. There is a square, each side being 4. The slant height of the pyramid is 5. That's all of those sides. And because I didn't use the dashed line, sometimes when you look at this, it can kind of like flip in and out as to where the base is and where the point is. It's just a visual illusion kind of a thing. So the slant height is 5. Find the surface area of the pyramid. So it wants the entire surface area. So we're going to start with the area of the base, which would be 4 by 4. 16, and then I need the area of all of the triangles on the side. Are they identical if my base is a square? Yes, they are. Now, they may not look like it in my picture, but if the base sides are all the same, then yes, they definitely are. So how many triangles do we have on the side? 4 of them, and they're all identical. And how do I find the area of a triangle? 1/2 base times height. What is the base of the triangle? 4. What is the height? Did they tell me the height? Oh, they did. I labeled it, no, slant height of the pyramid is 5. Right, I do not have the height of this. All right, so what we need to picture is the height from the center here coming straight up to the point. And since I do not have the actual other part, I need to draw here on the side so you can see that this is forming a straight line and then kind of like the radius coming across to connect. And then this is the given 5. So this number from here over is actually half of the full distance. So that's going to make this 2. And this is the height that I need. And the height coming straight down is always forming into a perpendicular, therefore 90 degrees. So what I've created here is a right triangle, and I need to find the height. If you remember, Pythagorean theorem solves for this missing piece. And I'm looking to see, are they taking you through that? Or did they do a different method? Area. All right, you know what? I'm going to stick with this. I'm not seeing quickly enough which method they're using here. So let's go ahead and Pythagorean theorem this, which means the two legs are squared and they equal the hypotenuse, the side opposite the 90 degrees. So this is 2 squared plus the h squared equals the 5 squared. So h squared equals 25 minus 4 is 21. The height, then to undo the square to get height alone, we square root. So that's the square root of 21. That is not an actual number, so we're going to leave it square root of 21. I am not seeing they're giving you that. I'm going to finish this way and then take another look at this example and see if I'm doing something incorrectly before we move on to part D. So what I would be filling in here is half base height, so the square root of 21. And then you're definitely going to calculator that to square root of 21 gives you a decimal times 2, basically, then times 4, which is your 8. And that is the sides, which you will then add with your 16 and get your total surface area answer. And I seriously doubt that's coming out what they said, 56 centimeters squared. All right, I wish there was a pause, but there's only, oh, wait a minute, maybe. Okay, in rereading the problem extremely carefully, I realized where I misread them. Okay. When I want the area of the triangles here on the side, and we want 4 identical ones of those, this is laying slanted. And so that means that this slant height of 5 that they're giving me here, it's not the side, it's actually this piece here, which is the height of that laying sideways triangle. So it did not need to go through all of this. This is something that you will do later, but basically this should be my 5 as the height for that particular triangle. Now we're back on track. 4 times 5 is 20, half of 20 is 10, 10 times the 4 is 40, plus the original 16 gives us 56. Dimensions were in centimeters, and now we match what they had at 56 centimeters squared. Okay, part D, spheres, the final one in this lesson. A sphere is your basketball shape. It's taking your circle and turning it into a 3D mass, making the sphere. They show you a picture on the bottom of page 22. A mnemonic, as their next darkened word there, is a memory aid. Now, they have a formula here which says, and it will match other math books, that the surface area, talking about all of the area around the sphere that covers its outside, and they use a formula 4/3 pi r cubed. You can use this. It is acceptable. It will work. I tend to not use this for the surface area. I tend to use the fact because it's just easier for me to memorize. Oh, wait a second, that's their volume formula. I was gonna say, wait, that's not right. Yeah. There is another one that I will use for the volume of a sphere, not this one, but it does work. The surface area one does match what this book says, and it basically is to picture the area of a circle and how many circles does it take to lay around to fill the entire sphere. That is 4. So you're basically doing 4 pi r squareds. And that's the surface area for a sphere. The volume of the sphere, can be this formula. I use the fact that a sphere is like a tennis ball encased in a can that's holding it. So I've got the ball inside and the can surrounding it, and the can only holds one ball. Then I need to shave off that extra spacing around the sphere that is not needed for the volume of it. So I treat it as finding the volume of the can that is surrounding it, which would be area of the base, circular, so pi r squared times the height. That is the volume of the can. Then matching the pyramid shape, which is why I find this one a little easier. I know that I should always have a third of it, but this one includes a 2/3. So what is shaved off is 1/3 of the can is not needed. 2/3 of it remains to be the ball shape. So I use this formula, 2/3 pi r squared times the height. But this is the same thing if you put them together and manipulate them. So even though this looks shorter, you are welcome to use it. I will tend to walk through this formula just out of preference. So on page 23, we get to example 7. Find the surface area and volume of a sphere, radius of 9 meters. So this is going to be in 3D. I'm only going to draw it flat, and the radius is 9. First thing it asked for was surface area. So that is going to follow the surface area formula. Pi r squared, which would be 9 squared, and then how many of those circles does it take to lay around? Times 4. So 9 squared is 81, times 4 is 324 pi, and then what were the dimensions in meters? So meters squared, because we were dealing in surface area. Then it asks for the volume of, so we're going to take pi times our radius squared times the height. Now, what does the height in a sphere look like? It is because the can that's it encased in is touching the ball, it's basically the diameter of the circle. So how much do I have here? 18, 9 plus 9 is 18, times 2/3. And that should take you to 972 pi. And again, volume meters cubed. And you'll want to do that on your calculator to verify that that is going to work out. Yeah, I can't do that in my head, but 3 goes into 18 6 times. 6 times 2 is 12. You're basically doing 12 times 81. All right, example 8. Find the surface area of a sphere whose volume is 288 pi. This one is, again, working backwards because they're giving you the volume. So what was the formula that got you to this place for the volume? That was your 2/3 pi times your radius squared times your diameter, or height, same thing. Yep. So now I need to work it backwards. So we're going to divide by this fraction, flip and multiply as we said before. So 288 times 3 divided by 2 gives you so much in pi, and that equals the radius squared and the diameter, which is 2 radiuses, if that's of any help. So then you can also take this number, divide it by 2, and get it down to be smaller. And then you've got radius squared times radius, which is basically giving you radius cubed. And you see how that gets very similar to this formula here. Equals, sorry, I'm having to shift kind of on you here. Then whatever this number in pi was, you need to cubed root it. So I'm going to see if I can get down to where they had it. Should be 216. And that means that I've converted that number by multiplying it with the pi. So then what is the cubed root of 216? And that is 6. So the radius comes out to be 6. Sorry, dimensions were in centimeters, so 6 centimeters. And that is the last example here in the book. Oh, wait, I just didn't know. Wait a second. This is not the final answer because it said find the surface area of the sphere. Once I know the radius, I then need to use the surface area formula. So I need to do 6 squared at 36 times 4. And then I can multiply that with the pi or leave it. They left it, so that would be 144 pi. And my dimensions were centimeters. And because this was surface area, we know it will be squared. So this was not the final answer. It shouldn't technically be boxed, but you get the idea, and that concludes lesson 2.